In today's video, we will explore Retrieval-Augmented Generation or RAG. The unflattering acronym was first coined by Patrick Lewis, lead author of the 2020 paper. The term now represents the future of generative AI. But before we delve into RAG, it's crucial to grasp a fundamental concept of vector embedding in AI. Let's say we want to sort things in the real world. We will organize them according to their similar use. Imagine a library or bookstore. It is common to see books on similar topics are arranged closely together. If someone is looking for a particular topic, you can help them find a book relevant to the subject by pointing in the direction of the shelf where the book is located. We can do the same in the digital world by using vector embedding, which is a digital way of sorting or representing things numerically. Each word is transformed into a multidimensional vector, typically between 200 to 500 dimensions, that encapsulates its context and semantic meaning. Although these high-dimensional vectors can be complex to understand, let's review a simpler example of color representation in the form of a vector. In a digital world, colors are numerically represented in the RGB system with a set of 3 numbers, each ranging from 0 to 255. Every color on your screen blends 3 primary colors, red, green, and blue. The RGB color code of value 89, 77, 181 represents a shade of purple. Here, you can see an example of the RGB system's 3-dimensional vector space with a few sample data points or colors represented based on their numeric values. Did you notice something special here? We can notice here that similar colors are grouped together in the same vector space, and the same colors are located close to each other. If 2 colors are different, they will be far apart, or the distance between them will be greater. Interestingly, we can do the same thing with words, paragraphs, stories, and web pages, where similar objects are grouped together in the vector space. A vector search determines the similarity between vectors using various mathematical techniques. The 2 most common methods are squared Euclidean or L2 squared distance and cosine similarity. Squared Euclidean or L2 squared distance calculates the straight line distance between 2 vectors. Its range is where 0 represents identical vectors, and larger values represent increasingly dissimilar vectors. Cosine similarity calculates the cosine of the angle between 2 vectors. Its range is where 0 represents identical vectors, and 2 represents vectors that point in opposite directions. So far, we have discussed vector embeddings and how they enable vector search to find similar objects efficiently. Now, let's explore how vector search enables the Retrieval-Augmented Generation system and how it helps LLM overcome the limitations of large language models. Large language models are trained on static data, which can lead to the generation of factually inaccurate or ungrounded information, a phenomenon known as hallucinations. Additionally, LLMs often provide generic information that may not be useful for users seeking personalized or context-specific responses. RAG combines LLM with your local database search to enhance the query results and make it more relevant to what a user is looking for. Let's break down the steps involved in designing a RAG system. Step 1. Data integration. First, all your local information, such as documents, websites, PDFs, or database entries, is fed into a vector database. This database converts your information into vector form, preparing it for quick retrieval based on similarity measures. Step 2. Query embedding. When a user submits a query, the RAG system intercepts it and immediately converts it into a vector using embedding techniques. This ensures that queries and local data are in the same format for accurate comparison. Step 3. Vector search. Now, the RAG system performs a vector search in your local database to identify vectors that are most similar to the query vector. It uses techniques like squared Euclidean distance or cosine similarity, which we discussed in our previous videos, to fetch the top 5 or more relevant results. Step 4. Information retrieval and query augmentation. The RAG system then modifies the original user query to include these top results as the context in the original query and then passes it to LLM for response generation. This means that the LLM doesn't rely solely on its pre-trained information, which might be generic. Instead, it now has specific, relevant local information to draw upon. Step 5. Enhanced response generation. With this enriched query augmented with additional information, the LLM now crafts a response based specifically on the local information provided. This results in answers that are not only more accurate but also highly tailored to the user's context. That's how a Retrieval-Augmented Generation system works to ensure that the answers provided by AI are as precise and helpful as possible. Thanks for watching. Please subscribe to the channel for future videos and updates.